Okay, is it working? Yeah. So hello everyone, welcome to our week 7 SPAM seminar. So our speaker today will be Andrew Beckett, who is a PhD student in mathematical physics from the University of Edinburgh. And he will be talking about symmetry, supersymmetry, and deformations in physics. So Andrew, please.
Hi, thanks for the introduction and thank you for inviting me to the seminar. So today I'm going to cover a number of different topics in physics with the same general theme. And I think I've been a bit ambitious with how much I tried to fit into this. So I think if there's time at the end, I'll bring it all together and talk about how it feeds into my research. But first of all, since I'm here representing the Maxwell Institute Graduate School, which is the maths graduate school in Edinburgh, I'll talk first about James Clerk Maxwell, which is named after. So James Clerk Maxwell was a 19th century mathematical physicist, and he was born in Edinburgh and studied in Edinburgh and Cambridge. And he's discovered quite a lot of things. I don't think he's very well known by people outside of physics, but there's quite a lot of important discoveries that he made. So the first one, which is kind of surprising because this is definitely not what he's known for, is that he discovered that human color vision is based on the colors red, green, and blue. So we have red, green, and blue color sensors in our eyes, and basically by kind of measuring everything that we see is measured in some amount by red, green, and blue, and that's how we see all the different colors. He figured out what Saturn's rings are made of and basically did this by mathematical modeling. So before Maxwell came along, people weren't really sure what it was made of. They knew it probably couldn't be solid because that would be horribly gravitationally unstable, and it would basically, Saturn would just pull the ring into it, or it would kind of crash against Saturn or something. And he figured out that it had to be made of small particles, essentially. And then the thing that he's really known about, which is what I'm mainly going to be talking about today, is he basically he was the first person to give a full description in mathematical terms of electromagnetism, so electricity and magnetism together. And importantly, he realized that they were really two aspects of the same thing, which we now call electromagnetism. And in the process of doing this, he also realized that light was an electromagnetic wave, and again he was the first to realize this. So James Clerk Maxwell is one of the few non-bastards that has a statue in a British city. So he has this really cool statue in the centre of Edinburgh, and actually I should point out, so here's him as a younger man. This thing that he's got in his hand is like a colour wheel that he used to demonstrate that if we see red, green, and blue light together, essentially it looks white to us. And then in the statue, he's holding this in his hand, and then he's got his little dog with him as well. And then there's some weird Greek stuff going on underneath him, which I'm not really sure what that's supposed to symbolise. But I don't think you can see it in this photo of the statue, but kind of on the ground by the statue, there's this plaque with his equations on, which I think is quite nice. So I'm going to be talking a lot about these equations. And so the first part of this talk is essentially going to be using Maxwell's equations to talk about different aspects of symmetries in physics. The second part I'll be talking about will kind of lead on from that. The second part leads on from that, but it's about symmetries in quantum field theory. And then the third part, I'll talk about how when we introduce gravity into the situation, it causes a lot of these things to curve and deform, essentially. And then if I've got time at the end, I'll talk about supergravity. So, starting with Maxwell's equations, this is what they are. They're some differential equations. They describe the electric and magnetic fields, which are two time-dependent vector fields in 3 dimensions. And it essentially describes how these things are produced by changes in each other and by charges and currents. So this first one, and I should say as well that a lot of this stuff that Maxwell was thinking about really didn't originate with him. So as you see, there's all these other people's names that are attached to these equations. And essentially, I think Maxwell's contribution was first of all to write them in something he didn't quite write them in this form, but something that's to basically to write them as differential equations. I think he was the first to do that, and he kind of put them together and realized what the significance of putting these equations together and what it told us, basically. So the first one is Gauss's law of, and it's misspelt, Gauss's law of magnetism. And it basically tells us that the magnetic field, so B is a magnetic field and E is the electric field. The magnetic fields don't have any sources or sinks. So unlike electric fields, you can't have magnetic charges. You can't have, or sometimes they're called monopoles. So whenever you have a magnet, basically it always has a north and a south pole. You can never just get an isolated north pole or an isolated south pole. And that's essentially what this equation says. The second equation says that the sources and sinks of electric fields are electrical charges. So this rho represents the density of electrical charges. And this E naught and mu naught that appear in these equations are just some constants. The important part is the rho here. So this is the electric charge. And then Faraday's equation tells us how changing magnetic fields produce circulating electric fields. So this is the principle on which electrical generators work, for instance. So as far as I'm aware, all but I guess except solar power. So most electrical generators work on the principle that if you move some magnets around, you'll change magnetic fields. They induce circulating electric fields, which can generate currents, essentially. And then this last one, the Maxwell-Ampere law, is the only one that really has Maxwell's name attached to it. So Ampere was the first to realize that, well, I don't know if I guess he probably wasn't the first to realize, but the first to describe mathematically how circulating magnetic fields are generated by currents, so by flow of charges. So this J in the equation is the electrical current density. And Maxwell added this other term, which is to do with the change of the change with time of the electric field. And Maxwell kind of realized that this was necessary to ensure essentially charge conservation, but it also kind of puts these two equations on the same footing with each other. So changes in the magnetic field induce looping electric fields, and changes in the electric field produce looping magnetic fields. And then the next really big step that he took was to put all these equations together in a vacuum. So that is when there are no charges or currents present. You get these two wave equations, so these second order equations. And if you've looked at waves, this is essentially the equation that's known as the wave equation. And by just looking at it, you can pick out what the speed of these waves would be, which is 1 over the square root of this product of constants. And these constants had been measured by people doing electromagnetic experiments, and Maxwell essentially realized that when you put these things together, you get the speed of light. And that was the first suggestion that light was an electromagnetic phenomenon. Before that wasn't known, and now it's and very soon after that it was kind of confirmed, and people discovered all kinds of electromagnetic radiation that wasn't visible light, basically. But this kind of causes a problem, and to explain why, I'll have to talk a little bit about symmetries in physics. So we often talk in physics about symmetries of theory. And these are transformations or changes which don't affect physical laws. So, for instance, Newton's second law, which I've written wrong here, so this should be the second derivative of x with respect to time. So on the left, I mean, I guess most people have probably seen this in some form, but on the left we have the total force that's acting on an object, and on the right we have its mass and its acceleration, if I've written it right. And this should be the same in at different times and at different places. So it's as true today as it was yesterday, as it will be tomorrow, and it's as true in Edinburgh as it is in Warwick. That might seem like a kind of trivial thing, but you could imagine, for instance, if part of this equation depended on position, for instance, then or it depended explicitly on position, then it would break this idea that the laws of physics should be the same in different places. And mathematically, we can describe this as the equations of motion that we use to describe things should be invariant under some transformations. So again, I've written this equation wrong, but the things which correspond to what I just said, it being the same at different times, is kind of summed up by the statement that if you the equation doesn't change if you replace t by t plus s, where s is just some constant, and it's the same if you replace x by x plus a, where a is some constant and some constant position vector. So you kind of shift everything. The equation stays the same if you do this. And then we can ask why are these things important? Why do physicists care about these? Well, first of all, they simplify problems. So, for instance, spheres are highly symmetric, and you much rather have to deal with a mathematical problem that's stated in terms of a sphere than just some general lumpy surface, right? And just the fact that it's symmetric means that there's a lot of things that we can do about it. So it's rotationally symmetric, so we can describe it in a nice way, basically. And although I won't really be focusing on this aspect, a big reason why symmetries are important in physics is because of their relationship to conservation laws. So this is summed up by Noether's theorem. And Emmy Noether is a kind of remarkable person, to be honest. So she was a Jewish woman in German academia in the 20s and early 30s. And because of that, she wasn't able to, despite being kind of brilliant, she wasn't able to get a full faculty position. She had some kind of lower level teaching job, but David Hilbert especially realized that she was a very good mathematician, and by the end of her life she essentially invented what we now think of as modern abstract algebra, and basically as a side project came up with this theorem. So Hilbert was interested in understanding energy conservation in general relativity, basically, and he set this problem to her because he knew that she was kind of dealing with some of the mathematics that would make it possible to understand this. And along the way she came up with this very general theorem about how continuous symmetries are associated with conservation laws. So for instance, this invariance up above of this time invariant symmetry is associated with the conservation of energy, and this spatial invariant symmetry is associated with the conservation of momentum. And this is kind of a fundamental thing that physicists use now, but it really wasn't understood until the 20th century, that these symmetries, which seem like kind of obvious things, are the things that make conservation laws happen, essentially. And these things these symmetries also provide the principles for building theories. So, you can write down any old differential equations that you like, but as a starting point, if you want them to make sense physically, they need to obey some of these symmetries that we expect with physical theories. So, I'm sorry, I don't have the kind of slow reveal here, but I just want to quickly say something about symmetries of solutions versus symmetries of theories. So what I was just saying was, these theories are described by some kind of equations, usually differential equations, and the transformations of these, and there might be some transformations of the quantities in these equations that don't change the equations themselves. And I just want to highlight that just because the equation of motion is, the differential equation is invariant under some symmetry, its solutions might not be. So for instance, if you're looking at the path of a projectile, obviously if you translate it, so if you kind of move its starting position, then you've changed to a different solution. You've changed to a solution where the projectile is starting at a different place. But that's still a solution. So the symmetries of the equations of motion will map solutions to solutions, but they won't necessarily map the same solution to itself. And then another example is that Maxwell's equations are rotationally invariant. So if you perform some kind of rotation on them, then you just get the same equations back. But if you take a magnet, which is described by Maxwell's equations, a magnet has a north and a south pole. So you get a vector that points from south to north or north to south. And obviously there are going to be some rotations that will move that vector around. So the magnet, this specific solution isn't invariant, but the equations still are. And, if you rotate a magnet, you still, you just get a magnet that's pointing in a different direction. So that's still a solution of Maxwell's equations. It's just not the same solution. Despite that, so solutions don't necessarily preserve symmetries. They certainly don't necessarily preserve all symmetries, but they might preserve some of them. So just for a really kind of dumb example, if you drop a mass straight down, then rotating around that axis doesn't change anything, right? So we'd say in that case that solution preserves that symmetry, whereas the magnet breaks rotational symmetry, for instance. And then just as a kind of health warning, I'm ignoring boundary conditions here. So usually when you're giving these problems with differential equations, you also have some boundary conditions specified. And you might want the boundary conditions to say that a symmetry really is a proper symmetry of the theory. You might want the symmetries to preserve the boundary conditions as well. But that's just an extra complication that I don't want to worry about too much here. Okay, so getting slowly back to Maxwell. To see why this thing about the speed of light is a problem, we have to start by talking about relativity. So basically from the 16th, 17th century up till Maxwell in the 19th century, and really 20th century, this idea of relativity was the same. So relativity is the idea that physics doesn't have a preferred reference frame. So all physical laws, such as Newton's laws of motion, should be the same in all inertial reference frames. So inertial just means that they're not accelerating with respect to each other. So if you have two people that are moving at different speeds to each other, and they're very clever people and they can do experiments and all these things, then they should come up with the same laws of physics. But somebody that's accelerating with respect to somebody else will come up with slightly different laws of physics, which is a slightly weird concept to think about, but I'll come back to that a bit later. Because it seems kind of odd that accelerating makes a difference. So in Newton, acceleration does make a difference, and as a result, you get some weird things like the centrifugal force or the Coriolis effect, because which is an effect on it essentially makes wind circulate because the Earth is rotating, and rotation is a kind of acceleration. And we'll kind of discuss how Einstein essentially got rid of this eventually. And changes of inertial reference frames include the kind of stuff that we were talking about before. So time and space translations, they also include rotations, and what are called Galilean boosts. So that's when if you have a coordinate system that's defined by one person, and then you have another person that's moving at some speed with respect to them. So, for instance, you have a coordinate system defined by somebody standing on a train platform, and then one defined by somebody that's sitting on a train that's traveling at a constant speed. This is the change between those two reference frames would be called a Galilean boost. And then when you do this kind of Galilean boost, velocities just transform in the way that you would expect. So, for instance, if you have two trains that are going parallel to each other, the person on the platform measures one train to be, let's say, going at 90 miles an hour. If you then boost to the reference frame of somebody on that first train, then the second train appears to be stationary with them, right? Because they're traveling together at the same speed, so they look stationary. So in this way, velocities add up, or rather, I suppose in that case, subtract. And that's something that we're kind of familiar with dealing with in everyday life. And under all of these transformations, time intervals, so the time between two events, and distances, and the lengths of objects, and these kinds of things are invariant. And the reason this is a problem for Maxwell's equations is this kind of idea of velocities transforming. So we saw that Maxwell's equations give you a prediction for the speed of light. The speed of light is basically a universal constant, or at least this is what Maxwell's equations suggest. So it then seems weird that if you say, if one person measures the speed of light to be what the speed of light is, right, and then somebody that's traveling at a different speed, this velocity transformation rule tells you that the second person that's traveling at a different speed should measure the speed of light to be something different. And there was a lot of debate over how you kind of deal with this in the 19th century, and a lot of people thought that there was this idea of a luminiferous ether. So there was some kind of background that light travels through. So in the same way that, you know, water waves travel through water, they thought, well, there's this thing that we call the luminiferous ether that light waves travel through. And to cut a long story short, this idea didn't work out. And Einstein eventually resolved this by saying, well, let's just take seriously this idea that the speed of light is the same in all reference frames, and go with it. So this is, if you like, this is kind of another symmetry principle, right? Everybody, no matter where you are, who you are, you should measure the speed of light the same, no matter what speed you're traveling at. And then you have to ask, okay, what do we change about relativity in order to do this? So turns out translations and rotations are fine. It's really just this idea about boosts. So we replaced this nice simple formula that I had before, which was x goes to x plus vt, to this complicated nonsense here, right? And this is called a Lorentzian boost, because this was, again, when this whole debate was happening, people weren't quite sure what was coming out. Lorentz came up with this formula. And this is a complicated formula, so I'm just giving the formula for a boost in the x direction. It's kind of difficult to do it in terms of vectors. So now, if you look at these boosts, it turns out that, first of all, I should point out that, have I lost, so if you look at this formula only makes sense if this v is less than the speed of light. So c here is the speed of light, and v is the speed of the boost. So if you look at the denominator here, it becomes imaginary if v is greater than c, or if the magnitude of v is greater than c. So this only makes sense for speeds lower than the speed of light. And it also turns out that if you do this, the speed of light actually stays the same in all reference frames, which is exactly what Einstein was looking for. But the cost that you get from this is that space and time don't stay constant. So time intervals, so under these kinds of boosts, time intervals don't stay the same and spatial intervals don't stay the same. So what that says is that people traveling at different speeds their clocks will run at different speeds and they'll measure lengths to be different. But this kind of combined quantity of the squared time interval minus the squared spatial interval is invariant. So you don't lose invariance completely. It's not just a free-for-all, but these things aren't invariant individually anymore. Yes, I already said this, and it turns out that Maxwell's equations are invariant under these transformations. So Maxwell inadvertently stumbled across the first special relativistic field theory before anybody knew anything about special relativity. So and that was kind of by accident. It just happens to obey these things. And so going back to Maxwell's equations, they have another type of symmetry. So everything I've been talking about so far is space-time symmetries, where you move things around or you rotate them or you measure them at a different time or something like that. And these have a slightly more kind of abstract symmetry. So if we take two of these equations, so this first one, Gauss's magnetic equation, it tells us that we can write the magnetic field in terms of vector potential. So because its divergence vanishes, it has to be the curl of something, basically. And then likewise, you can do this takes a bit of rearrangement to figure it out, but you can write the electric field in terms of the same so-called magnetic potential, and an electrical potential, which is a scalar field. So this is just a real function on R3. And then for any function of space-time, so this is again a function of a time, if you can think about it as a time-dependent a time-dependent function on R3, then this transformation of the two potentials leave the electrical and magnetic fields unchanged. And this seems like okay, you know, why do you care? This is even less of a you know, obviously sensible thing to talk about than space-time symmetries. But it turns out that just by saying that you want a theory to have this property, you have to have electromagnetism, basically. And I'll come back to why that is later on. Okay, so before I move on to symmetries and quantum field theory, has anybody got any questions about the stuff I've been saying so far? Okay, I'll go on then, if not. So, what we've been talking about so far are this idea of equations having these symmetries. People were thinking about this all along the way, but there wasn't really a point where people were really thinking, let's start with the symmetries and then try to write down the equations based on the symmetries. Basically, let's try to write down some equations that obey these symmetries and then see if they give us something physically correct. And the first person to actually put this into practice was Paul Dirac. So he was working at the beginning of the 20th century when all of this stuff about relativity was being discovered. Quantum mechanics, which we haven't mentioned at all so far, was also being thought about, and that comes along with its own symmetry properties, along with a load of other principles. And Dirac wanted to essentially put all of these things together and see what happens. So there'd been some less successful attempts at putting all of these ideas together about the same time as Dirac, but Dirac was the first one to really manage it. So he came up with this equation. So I won't fully go through exactly what's going on here, but this is the kind of variable in this equation is this function psi, and it's a function of time and space again, but this time it takes values in C4. So it's a four-dimensional complex vector, and then this m is a particle mass. This h bar is some is a constant which comes from quantum mechanics. This I is the imaginary I, and then this alpha I and beta are some 4x4 matrices that are based on some properties. And okay, I won't go through the details of this, but this equation, again, just based on the symmetry principles, gave the first quantum relativistic description of a free electron. So that is an electron that's not kind of interacting with other electrons or in the presence of some external electric field or something like that, which was what he was aiming for. But it also, basically by accident, gave an explanation for the origin of spin. So you might have, if you've heard anything about quantum mechanics, you've heard of this idea of spin, which is kind of an intrinsic angular momentum that particles have. And in quantum mechanics, in ordinary quantum mechanics, it's kind of just put in by hand because people found it in experiments and thought, okay, how do we describe this mathematically? And Dirac kind of showed that it just comes directly from the principles of special relativity. And also, along with spin, there's this idea of the Pauli exclusion principle, which is really important because the Pauli exclusion principle essentially says that two electrons can't sit on top of each other, so they have to be separated. They have to be in different states, so they essentially have to be separated somehow. And then that principle means that atoms then have some structure, which then means that you can have matter. Essentially, you can have things like solids, liquids, and gases, and it's not just kind of a degenerate gas of electrons. And it also predicted the existence of antimatter, which was a complete accident. So this equation only works if, as well as the electron, you have this kind of negative thing called the positron or the anti-electron. And then a decade or so, I think, after Dirac, that thing with the positron was actually observed in experiment. Okay, so going back to this idea about gauge symmetry, which I was talking about with the Maxwell equations, what can we add this to the Dirac equation? So the Dirac equation already has what's called a phase invariance, which is something that comes from quantum mechanics essentially, and it says that if you change something by a unit, if you multiply this field or this wave function by a complex phase, so by a complex number with length 1, then it doesn't. The equations are invariant, so physics doesn't care if you do this. Basically, this is a change that you can make. It's a transformation of the equations that you can make. But here, this phase theta is constant. But if you remember when we're talking about the gauge symmetry in Maxwell's equations, the thing that you were changing things by was a function. It wasn't just a constant number. If we try to upgrade this thing to a function in Dirac's equation, so if we do this transformation in Dirac's equation where theta is a function, basically because there's some derivatives and stuff going on that don't vanish, the equation is not invariant. But you can force the equation to be invariant by adding an extra term to it, and it turns out that if you add this extra fields to the equation, so you already have this one field, this psi, you have this thing called A, which includes the data about a time-dependent vector field and a time-dependent scalar field, which transform with the transformation properties that we had in electromagnetism. Then the new equation is invariant. So, and this is kind of and it turns out this is kind of the only thing that you can do. So what I'm saying here is that if we want Dirac's equation to have this same gauge symmetry as electromagnetism, then we have to change the equation in such a way that that you cancel out the transformation. And the only way that you can do that is by adding this thing which looks like the electric field essentially. And when you do that, the electrons now behave like charged particles because you've introduced this coupling between the electron field and this electromagnetic field, and A has to behave like the electromagnetic field. And what you get is what was essentially the first quantum field theory, which is known as quantum electrodynamics. So taking these principles further over the next basically 50 years, I suppose, through most of the 20th century, you end up with what we have now, which is the standard model of particle physics. So this is based largely on experiment. There's a lot of experimental work done to come up with this, to discover all of these new particles. But to really understand what people were seeing, they had to use these symmetry principles. And this standard model is based on the stuff that we've been talking about so far, so special relativity and gauge theory. And the gauge theory really works to organize these particles into families. So you see they're kind of organized into these different families called quarks and leptons, and they're all kind of color coded, and they've got these and they're arranged into this table. And essentially, to get this arrangement, to get this description here, you need these symmetries to understand how this structure comes about. And it also constrains the particle interaction. So in exactly the same way as I was talking about, you kind of have to introduce electromagnetism to make Dirac's equation gauge invariant. In the same way, to have gauge invariance, the interactions between these particles have to take a very specific form. So that then predicts the way that these things are supposed to interact with each other. It predicts new particles, because if you try to do if you try to introduce a symmetry and it turns out that there's some, in order to make the symmetry work, there's some stuff missing, that's then a prediction of new things that you didn't know about before. And those things were observed eventually, those things that were missing when people tried to come up with these symmetry principles, they were all observed. So the Z bosons and W bosons, which are to do with some nuclear forces, and the Higgs boson were really part of this missing symmetry idea. So these were predicted essentially mathematically first, and then later on they were seen in particle physics experiments. And the other big organizing principle in this table of the particles that you have in the standard model are that it's divided between fermions, which are particles that obey the Pauli exclusion principle. So as I said, this Pauli exclusion principle is important for building up matter and actually having structure in the universe. And then the bosons, which are force particles. So you see here the photon, which is the particle of light, and then all of these other bosons, which are associated to different gauge symmetries. So they're called the gauge bosons. And then the Higgs boson as well. These all don't obey the Pauli exclusion principle, but they're important in physics because they essentially they mediate the interactions between these things. So two electrons kind of know to be repelled from each other, for instance, because they exchange some photons, which are kind of like messenger particles. And I'm aware that I'm running out of time, so I'll just say this quickly. Actually, how much time do I have left? Do I have about 5 minutes?
I guess you can still have 15 minutes maybe. So.
Oh, 15. Okay, good. Okay, that's good. Standard model is very successful. It describes the constituents of all kind of ordinary matter. So anything that you interact with on Earth essentially is made up of is described by the stuff by the particles and the interactions that are in the standard model. It describes all the microscopic forces. So that includes the electromagnetic force and the nuclear forces, so the things that hold atomic nuclei together and cause nuclear decays. And it also successfully predicts, I think, all particle collider experiments to date. So anything that's been, especially for the last decade or so, people have been trying to poke holes in the standard model and find problems with it. And essentially by doing particle collider experiments, they haven't found anything that doesn't obey the standard model, basically. And that's both, I mean, it's a good thing because it says that we're on the right track, but it also says that it's also a problem because it doesn't provide anything new, basically. It doesn't tell us where to go in terms of understanding other things in physics. And the reason why, the reason this is a problem is because the standard model, although it describes all ordinary matter, there's a lot of stuff that it doesn't explain. So for instance, I won't really have time to go into this, but there's stuff called dark matter and dark energy that's observed in astronomical observations. So essentially, if you only account for the ordinary matter that's described by the standard model, then the things that distant galaxies seem to do make no sense, and observations of the early universe don't make any sense. There has to be some more stuff there that's providing more gravity. So that's dark matter, and then dark energy is kind of an extra thing as well, which seems to be causing the universe to expand, and not just to expand, but for its expansion to accelerate. And then there are other kind of technical issues to do with this. So there's still some stuff about particle masses that isn't really understood, and a thing called the hierarchy problem, which is basically that the electromagnetic force is a lot stronger than one of the nuclear forces, which is called the weak force. So that's the thing that's associated to the Z and the W bosons. And then it's also, and then the electromagnetic and the weak force are massively weaker than the so-called nuclear strong force, which is the thing that kind of binds nuclei together. And nobody really understands why these forces have such different strengths. It's many orders of magnitude difference in strength. And then gravity is even weaker than the weak force still. So that's something that nobody really understands, because these things are supposed to be described by the same theory. So it's not clear why there's this massive discrepancy in their strengths. And then there's a load of other more technical stuff about quantum field theory that the standard model doesn't seem to resolve. But one solution to all of these things is a new symmetry. So everything I've talked about so far is kind of building on symmetries that people already knew existed, these space-time and gauge symmetries. And this new symmetry is called supersymmetry. So I've already said that these particles are divided into two types called fermions and bosons, so the matter and force particles. And supersymmetry essentially suggests that for each one of these particles, so for each matter particle, you have what's called a superpartner. So a boson, which is a force particle, which kind of has it has the same properties, except it's a boson where the original particle is a fermion, and then vice versa. So on the left here, we've got the standard model particles, and on the right, we have their hypothetical superpartners. So the superpartner to bosons and fermions, the superpartner to fermions and bosons. Again, when you actually look at the mathematics of these things and really drill into the equations, what supersymmetry is doing is, again, so in a sense, it's kind of swapping fermions with bosons in a particular way, in such a way that it leaves the equations unchanged. But in order to do that, again, it heavily constrains the particle interactions, even more so than the symmetries that we've been talking about so far do. So they give us very specific ways of writing down the equations, and there are loads of different kinds of supersymmetric theory. Supersymmetry isn't a single theory; it's essentially a property that a theory can have. So this is showing what's called the minimal, or this kind of cartoon picture of the minimal supersymmetric standard model. So it's kind of the simplest version that contains the standard model but has extra stuff and is supersymmetric as well. So I think I'll come back to supersymmetry in a bit. Again, okay, I'm moving on to a new section now. So does anybody want to ask questions about what I've said so far? Just while I get a drink.
I have a very quick question. I'm no expert by no means. I mean, I completely do other things. So it seems like we're adding into our model of trying to understand particles and the physics of the world. In order to explain more and more, we try to add more and more. Was there, was there any ever thought, or is anyone in the world trying to come up with something new that we haven't seen, yet in the standard model? Or is that too much effort and a waste of time to sort of, since most of it is explained?
Yeah, so that's a very good question. Thank you. So there's actually quite a lot that I could say about that. So the first thing is that, especially this stuff about gauge symmetry and these kind of and other kinds of internal symmetry, so things that aren't to do with space-time, they originally came about as a way to explain why we saw so many different particles. So the fact that we've kind of boiled this down to, what do we have here? I mean, it depends how you count, but, we've got an order of about, 13 particles here. In the 60s and 70s, when this became a problem, people were seeing hundreds of different kinds of particles, right? Literally every day, new particles being discovered in colliders. And they seem to have, and when you plotted these things out in terms of, okay, what are their masses and what are their charges, people were saying, okay, there are patterns here. These things seem to lie on these on lines, and they make these kind of weird patterns in the data. So there's something going on here, but we don't understand where all this structure is coming from. We don't understand what these particles have to do with each other, why they seem to correlate in these ways. And it turned out that what was actually happening was that all of these particles that they were observing were actually they were composite particles, so they were made up of more fundamental stuff. So all of these ideas about symmetries and whatever came from literally seeing patterns in the data to begin with, or at least this idea of applying these symmetries to particle physics. And then there was I think in the 70s, Murray Gell-Mann came up with this idea of quarks, which was supposed to be these more fundamental particles. And at the time, I think he thought they were a mathematical trick. He didn't realize they were real particles. But he basically came up with this as an organizing principle to understand these patterns in the data. And then eventually people started to really think that maybe these quarks actually are particles themselves. And then it turns out that all of these kind of hundreds of different particles that they were observing were were quarks existing together in different combinations and at different energy levels and stuff. The other thing is that so in that sense, we're not really adding to stuff more and more and more. especially in the 20th century, it was more and more and more was being discovered by experiment, and then the theorists came along and said, actually, we're not really seeing new stuff here. We're just seeing more aspects of this more fundamental stuff. So when people managed to break it down in this way and explain things in terms of quarks, the picture became much more simple, and they actually reduced the number of particles by orders of magnitude that they were dealing with, and they understood the relationships between these particles a lot better. And then in terms of looking for new stuff, that is something that's happening all the time. So people are looking for ways that these theories go wrong. So they're looking at the kind of unexplored territories, types of experiments that haven't been done before, you know, looking at properties of particles that aren't very well studied, and trying to find places where the way these things actually behave is deviating from the standard model or deviating from some other like physical models that we know about. And then this stuff about dark matter and dark energy, although these are kinds of like, these are like you know, I don't know, describe them as substances maybe that exist out in the universe somewhere. They're very difficult to detect. We've never actually been able to, you know, pin down a lump of dark matter or even a single particle of dark matter and figure out what it is. So there are lots of theories about what it might be. And part of, so the reason why supersymmetry is kind of popular is because of this nice symmetry property. It deals with a lot of these weird mathematical or theoretical issues that people have with standard model, but it also provides this new kind of collection of particles that might make up dark matter, essentially. And I should say, for just to be completely honest about this, in the last few years, the kind of this, especially this minimal supersymmetric standard model, or the version of it which people were most excited about and they thought might solve all of like a lot of these problems in basically with one idea, has basically been ruled out by experiment. It seems like basically by a combination of astronomical observations and particle experiments say that this idea doesn't really work. So supersymmetry isn't necessarily going to save us from a lot of these problems in the immediate future. And people now are looking at a lot of different ideas, because people say supersymmetry is dead. I don't think it is, and a lot of people don't think it is, but certainly the most promising supersymmetric theory that was available is no longer favored. So people are looking at all sorts of different ideas, especially in the last few years, because this has started happening.
Amazing, thank you.
Yeah, and thanks for the question. It was a really interesting question. Okay, so I'll go on to talk about gravity a bit now. So we haven't really talked about gravity at all yet, and that's because it kind of sits aside from all of these other things. It was just nobody had really done much with gravity. I mean, okay, I don't want to overstate the case, but gravity was basically the same since Newton. So all of this stuff about electromagnetism was really discovered and refined after Newton came along and realized how the basic laws of motion and gravity work. But then as a result of this idea of special relativity that kind of span off from electromagnetism, Einstein realized that gravity needed to be rethought. And essentially it's because in the same way that Einstein's equations weren't compatible with Galilean relativity, so Einstein had to invent special relativity in order to deal with it. On the flip side, gravity is really grounded in Galilean relativity, so it doesn't work with special relativity. And one way of seeing why this is the case is by thinking about Newton's law of gravitation, which is essentially just sums up everything about Newton's theory of gravitation. So any two masses in the universe feel an attractive force between each other, and this force is given by this equation. So r is the distance between them, m1 and m2 are the two masses. Sorry, this comma shouldn't be there, and g is a gravitational constant. And this, even Newton realized this was a problem, but it wasn't really resolved for hundreds of years up to Einstein. So this seems to suggest that no matter how far apart two things are, they know about each other, right? Because they feel this gravitational force. So if you move one thing about, the other particle feels it instantaneously. Or if one, if the sun were to disappear one day, for instance, we would immediately know about it on Earth because the gravitational interaction would suddenly have disappeared. And this is referred to as action at a distance. And the way this was kind of partially resolved was by thinking about gravity in the same way that we thought about electromagnetism. So in electromagnetism, you have charges which produce fields, and the charge kind of produces a field around itself, and then that effect propagates out. And in the same way, in gravity, you think about a gravitational body like the sun producing a gravitational field around itself that then propagates out. So it's not really action at a distance because it's not two things physically interacting with each other at a long distance. It's one thing produces a field which propagates through the universe, and then other things experience that field basically. But still, in the mathematics, it seems like if the sun disappears, even with that kind of shift in the mental picture, the mathematics doesn't change. If the sun disappears, we still know about it immediately. And that's a problem in special relativity because the invariances of special relativity and this stuff about, like I showed you, that boosts can only happen at the speed of light. That's just a general rule. Things can't travel faster than the speed of light, and information and the influence of one object on another can't propagate faster than the speed of light. So it takes light 8 minutes to get from the sun to us. So anything that happens on the sun, we better not know about it. We better only know about it 8 minutes later, basically. Special relativity is violated if that doesn't happen. So this is the problem. And Einstein realized this, and he was also interested in extending special relativity to non-inertial reference frames. So I talked about this idea of two reference frames accelerating or not accelerating with respect to each other. Einstein said, what's special about accelerating reference frames? We want laws of physics that are really true in all reference frames. We don't want to worry about this inertial versus non-inertial or whatever. And that this is really where the dichotomy between, this is why special relativity is called special relativity, because it's about inertial reference frames, and then general relativity is about all reference frames. Okay. So I'm running out of time, so I'm going to skip Einstein's argument for how this comes about. But the punchline of how Einstein deals with this, and sorry that I'm just kind of skipping over this, but is that we have to start thinking about space-time as curved, essentially. So if you think about space-time as, we tend to think about space as a three-dimensional thing which changes over time. And what Einstein says is, no, you have to think about it as a whole four-dimensional space-time. And at any given time, you have a three-dimensional slice of space. And the presence of masses in space-time causes space-time to curve. So this is kind of a cartoon picture. It's not fully accurate because you might have seen this before. So the idea is, you put a bowling ball in the center of a rubber sheet and it bends downwards. So it's as if the presence of mass is causing deformation and curvature. This isn't quite what Einstein is suggesting, but it's a nice enough analogy. So you just have to think about it kind of in 4 dimensions. And this kind of does away with the idea of gravity as a force. So instead of gravity being a force that one object exerts on another, gravity is just the name that we give to the effect that when objects exist in space-time, they curve space-time around them, and then other objects that are trying to move through space-time in a curved space-time, in a curved space is the equivalent of a straight line, which is called a geodesic. Those lines appear to be curved because space-time is curved. So essentially, everything is just moving in straight lines all the time. If it's not under the influence of other forces, if it's only moving under gravity, everything is just moving in a straight line through space-time all the time. It's just that space-time itself is curved, which is why it seems like things curve towards the Earth or go into orbit or something like that. And okay, I'm sorry. So I mentioned deformation. So I've met all the keywords in my title. So I'm happy to finish there. Thank you
very much. So before we move to a quick Q&A session, let's unmute ourselves and applaud for Andrew's interesting talk, please.
Thank you.